Okay, so the topic then for the next hour is to talk about some fundamentals of matrix algebra, because that's fairly essential for any type of computational probabilistic modeling, and especially, of course, the GLM as well. So before we start, maybe to check, so let's say you have these two matrices, maybe something like that. And you're supposed to multiply them. So who of you would know what to do here? Please raise your hand. Okay, that's... Can you really raise your hand? That's a little bit hard to see. Okay, so a couple of you. Okay, but for the majority, this will actually be novel. Okay, and this is actually the crucial thing, or the most maybe complicated thing to get your head around matrix multiplication. Or the rest in terms of matrices is actually pretty simple. Yeah, so then for everyone who doesn't know how to do matrix multiplication, this is then your intro to matrix multiplication. So first of all, definitions, what are matrices? So topic of this hour now, matrix algebra. First thing, definition, what is a matrix? And then we will talk about matrix operations. So basically calculating with matrices. Specifically, we will talk about addition and subtraction of matrices. And then we will talk about scalar multiplication of matrices. So that will be a brief topic. Then we will talk about, and this is, like I said, that's essentially the core of the whole thing, matrix multiplication, which is something you need. This is, in a way, in this beginning and all my mathematics teaching, this is all more like knowledge, but matrix multiplication you have to actually train yourself a little bit in so that you get fluent with that. Then I will tell you, at least conceptual, what matrix inversion is. And we close on matrix transposition. So these are the things that I want to familiarize you with. And we start with the definition of a matrix. And that's pretty straightforward. So a matrix is a rectangular collection of numbers. So I now define a matrix here, A, as a rectangular collection of numbers which get indexed by a row and a column index. I will explain that in a second. So like this, and it has these brackets. My brackets are really bad. I have to learn how to get automatic brackets. So a matrix looks somewhat funky. I'll just put that up here. A matrix is a rectangular array of numbers. So it extends somehow the concept that you are familiar with of a number. So for now, numbers or the things that you compute with, not numbers, but the things that you compute with. So you are familiar to compute with scalars, so single numbers. You know how to add 10 and 12. You know how to divide 2 by 3 or something. But you maybe have not computed with matrices. And in mathematics, you can compute or at least manipulate and interact with different entities. And one such entity is the concept of a matrix. Matrices are fairly important in computational or in scientific computing, data analysis and whatsoever, because they, first of all, you can compute with them, and secondly, they are also an efficient way to store, in a way, data sets. So you can, so what you've seen, I guess, if you haven't seen matrix multiplication, you have seen your SPSS table. There were rows and there were columns, and the columns were I don't know, variables, and the rows were participants in your study. So there you actually defined a rectangular array of numbers, and it had some meaning, and essentially you defined a matrix. So, so what about this notation here now? So this matrix consists of elements which are indexed with a row and a column index. The row index comes first. That's the row. And that's the column. I think there are two things to learn about matrices. One is how to multiply them, and the other thing is to really get into your ingrained in your nervous system that the row index comes before the column index. Once you are fine with that, you're fine with matrices essentially. These row and column indices are natural numbers. And actually, what this means, what I just wrote, is that this I, row column index, is larger or equal to 1 and smaller or equal to n. So basically, you can also express this as I goes from 1 to n, which means it goes from row 1. So we can also write it like this: 1 to n. So that means that there are n rows, so that's our n here, and the j goes from 1 to m, so there are m columns, so that's m. Yeah, so you see 1, 2 going on to m. Yeah, so a matrix always has n rows and m columns, and a specific matrix, for example, the matrices that I wrote up before, maybe as a little quiz, how many rows does this matrix have? And how many columns? Yeah. So this, in this case, the n would be 2, and the m would also be 2. And of course, one can also write down 1,000 times a million matrix, so 1,000 rows and a million columns. One can also write down a 1 by 1 matrix. So that would have 1 row and 1 column, so it's a scalar. So just a single number. So there are many matrices, and the matrices we are interested in are matrices with real entries. The numbers that also, so the values that these elements of the matrix can take on are real numbers, the most crucial thing about matrices is that you can index them. So, for example, if we have this matrix here, this element here is in the second row and in the first column, so it gets these indices 2 and 1. Yeah. What's the so what are the indices of this element? 1, 2, exactly. And this is of course 2, 2, 2, 2, Dougie Jones. 2, 2. And this is 1, 1. Yeah, so this is something to get used to, especially focus always on the fact that the row index comes first and then comes the column index, and the index runs from 1 to n, or you can also, you don't need to call the number of rows n, but most of the time I will do that, and the number of columns m. In general, to write quickly that A is an n by m matrix with the real numbers as potential entries, I will use this notation. So there's a matrix A, and it is an n by m matrix. Yeah? So this is what this should mean. So for example, if I write something like A this, what you should think of, okay, A has 2 rows, so that's the rows, and 3 columns. So in general it looks like this, so 1, 1, A, 1, 2, A, 1, 3, so 3 columns and 2 rows, A, 2, 1, A, 2, 2, and A, 2, 3. And these A's here, so these A, I, J, for A from 1 to 2, it's not that far actually, and J from 1 to 3, they are real numbers. Yeah. So that's the notation that I will always use. If actually n equals m, so like in this case, you see that this is actually not a rectangle but a square. So these are called square matrices. So that's what a matrix is. It's something that we actually write down here on this fancy new tool. And you can also write down on paper. You can also do a LaTeX version of this, but it's an abstract thing. So especially if you start programming, try to separate matrices in mathematics and arrays of numbers that you are dealing with in programming from these mathematical matrices, because once you start programming you will find that you can do things with arrays of numbers that you can't do with matrices, and then you get confused. So the matrices that we're talking about, they are abstract concepts that we can write down and talk about. Yeah? They are not necessarily the matrices that you've first encountered in programming. Good. Now that would be a little bit boring if we can only define a matrix as such a rectangular array. Other questions? Yeah.
Sorry. What was the last thing you said?
The last thing, I forgot. I should rewind. What? So the abstract concept in terms of programming versus math. Well, it's different things. So I think it will get clear once you get an introduction to programming that that there are things in programming that are also called matrices, but they are not necessarily mathematical matrices. So I'm just trying to warn you that this is something different. Yeah? But I will come back to that when we do our introduction to programming. So for our purposes here, matrices are these abstract things that we write on the board and can talk about. Okay, anything else? No? Good. Then, so this was our definition. Now we want to actually compute with that. And of course, you know how to compute with scalars. So you know if you see something like this, 2 plus 4, you know that this is 6. And actually know how you know that, or at least I don't know how I know that, but I know it. These kind of things, so basically to compute with mathematical entities, this one can also define for matrices, and we will go over things that you can do with matrices step by step. So the first thing that you can do with matrices of the same size is to add or subtract them. Yeah. So the first thing would be, so we are now at addition, subtraction of matrices. The first thing that needs to be fulfilled if you want to, if you have two matrices and you want to add them, so we now have two matrices A and B, this only ever works if they have the same size, yeah? So A needs to be, well, A can be whatever it wants in a way. Let's say it's n times m. But now to add B to it, B also needs to be of that size, yeah? So for example, if A is a 2 by 2 matrix, you cannot add a matrix that is 2 by 3 to it. And that's just definition. And it makes, it will become really clear why this is the case. Because addition and subtraction from matrices is an element-wise procedure. So let's write out what our A and B are. So A is our first matrix to M and N1 A N M. So these dots, actually I didn't explain these dots. These dots are like, you should fill in the appropriate thing in your head. So here the index increases over rows, and in the other direction the index increases over columns. So B, as I said, needs to be the same thing. So B, in this case, not the same thing, but the same matrix size. So it needs to be of this size. Oops, that's of course an element of B. We call B N1, B N M. And then if this is fulfilled, so if we have two matrices of the same size, we can actually add them. So A plus B is then defined as the matrix in which you add the elements. Do the same thing everywhere. Here you have A 1M plus B 1M. Paper never runs out on this thing. It's amazing. A N1 plus B N1 and A N M plus B N M. Gets a little bit hard to read, but you have the nice LaTeX version of the whole thing. So that's really simple. So let's do an example. If we have A equals 2105 and B equals, or is defined as 4012, you can compute C as A plus B, which is what? So how big is it? What kind of matrix is it? It's a 2 by 2 matrix, and what's the first entry in the first row? The first 6, exactly. And here on the next one, 1, exactly. Here, 1 and 7, exactly. So that's matrix addition. Same thing for subtraction. So if there's a, maybe let's do that. If there's a minus sign here, the same thing, the same rules apply. So what do you get? Minus 2, exactly. Then 1, exactly. And then minus 1 and 3. Yeah. So simple enough. That's matrix addition and subtraction. Only works if the matrices have the same size. Yeah. So if they don't have the same size, it's not defined. You don't have to worry about it. If you have to worry about it, you just have to do it in an element-wise manner. Good. Next thing, also relatively simple, scalar multiplication. That's already an interesting thing about matrices. So when you think about working with numbers, you were used to adding numbers and multiplying numbers. But if you multiply numbers, there was only one way to multiply numbers. You just multiplied them. So 2 times 3 is 6, and that was it for multiplication. For matrices, there are two kinds of multiplication. The first and simpler one being scalar multiplication. So if you have a matrix A that is of a given size, n times m, one can define the scalar multiple of it. So for this you need a scalar, so just a real number, which of course is also a 1 by 1 matrix, but actually, if we are doing it the sloppy way, if you do it the linear algebra way, then it's a bit different. Anyway, so it's just a real number, so something like 2 or pi. Based on that, one can now, based on these two things, one can define what is called the scalar multiple of a matrix. What that means is, again, an element-wise procedure. So you have the scalar times the matrix, and that corresponds to C times each element. Yeah. Oops. How many columns? M, C, oops, completely wrong. C times, we'll put a little times in there, 1 m, C times n1, C times a n m. So, as an example, if we have a matrix A being 2, 1, 0, 5, somewhere like this, and C being 2, again we define A and C like that, then we can compute B as C times A, which we can write as 2 times 2, 1, 0, 5. And now this is the rule that we should apply. So what do we get?
4, 1, 0, 10.
4, exactly, yeah. 0, 10. Exactly. So that's a scalar multiplication. That's also quite straightforward. Yeah. So now you already learned 2 operations, or maybe 3: addition, subtraction, and scalar multiplication. So now it's time for the real deal. So now we talk about matrix multiplication. In a way, you can think of matrix multiplication as a useful way to write weighted sums. Maybe that whatever, but that's one way to, because you will need so matrix multiplication needs a lot of weighted sums. So what do I mean by weighted sums? We've seen sums before, and you now if you have a product here, so let's say you have an I and you have an X I, and you want to compute the sum. So you want to compute something like A1 times X1 plus A2 times X2, and you want to go on with that until AN times XN and add them all up. And you want to do that many times. Then you might think about using matrix multiplication and arranging stuff in an appropriate way. So that just as a side note. First of all, you cannot just multiply any kinds of matrices. They need to fulfill certain conditions. And the basic condition they have to fulfill is that the first, so if you write down a matrix, so if you have two matrices, A and B, and you want to define their multiples, so which you can put a dot there, but usually I don't. Then a certain condition needs to hold, namely A must have the same number of columns, so A is n times n, as B has rows. So these two numbers, and in this order, so if you have A times B, the inner, if you want, sizes need to be the same. Yeah. So A has to have m columns and B has to have m rows, which is also already then means that that is a little bit different from what you were used to, because you were used to that 2 times 3 is the same as 3 times 2. But if you now commute here the matrices, what you will see is what you have here is that you want to multiply a matrix with p columns to a matrix with n rows. That doesn't work, yeah, unless p and n are the same number. But because they're different symbols, we can safely assume in general that they are different numbers. Okay, so this is the condition that needs to hold. So to compute the matrix product like this, A needs to have m columns and B needs to have m rows. N and P are free to vary. And then, yeah, I will first write down the matrix product, how it is defined, and then give you an intuitive way to compute matrix products. So let A again be matrices as previously. So something like A1 1 to A1 m and A n1 to A n m, and B being B1 1 and now B1 P, so P columns, and M rows, so here B M1 to B MP. So if these things are like that, then A, B corresponds to the following. You need sums, and you sum, let's make it like this, you sum always from 1 to m, yeah, so this m, and for the first row and column entry of AB, what you take is you take the first row of A, so you take A1I, I goes from 1 to m, so you have all these elements here, and you multiply them with all the elements in the first column of B. So you take B I1, and that's basically that's the first entry in your resulting matrix. For the next entry, so the entry at row 1 and column 2, you again, and this will be all the time, you sum over m, and again you take the entries in the first row of A, and you multiply them with the second, the entries in the second column of B, and you go on for that with that until you have done it for all columns of B. So you are still taking the first row and then at one point you have applied essentially the first row to the last column of B, and that's your last entry in the first row. Yeah, so that's the first row of the matrix product. For the second row, you always sum from 1 to m, but now you take the second row, so basically what's written here, of A, and do the same thing again over columns of B. Yeah. So always from 1 to m, taking the second row of A, until you are again at the end of the columns of B. So you go on with that over all rows of A until you are in the last row. So you are at ni, and multiply this, multiply each entry of this last row of A with each entry in the first column of B. And you go still from 1 to m, and you do that the same thing here again until you at the very last entry of your resulting matrix, finally where you use the last row of A, and you use the elements of the last column of B. So this is of course still part of the resulting matrix. So that's how the matrix product is defined. Now that looks like many sum formulas, and these are essentially many sum formulas, and they are weighted sums because you always multiply the elements in a certain row of the first matrix with the elements of a certain column in the second matrix. And actually this sum formula, it's good to have seen it, but actually practically it's more like a mechanical thing that you need to get used to, and I will show you what I mean by that. So, and this is something you should actually train yourself in these weeks, in these early weeks of the winter term. So as an example, I will show you what I mean by mechanical thing. So let's assume we have two matrices, which actually, where the first one has as many columns as the second one has rows, and they take, in this case, this form: 2, -3, 0, 1, 6, 5. And B, and we want, B takes this form: 4, -1, 1, 2, 0, 3. So we see that we can actually multiply them. And now what you have to do in your head, or somehow mechanically, is that you need to take, to now compute the entries here, you need to take these elements of the first row of A and basically rotate them by 90 degrees in your head. So put them in your head, you can also do it on paper, next to these, and then multiply them, and then add up the resulting thing. So in this case you would take 2 times 4 plus -3 times -1 plus 0 times 1. So that would be 8 plus 3 plus 0. So that would be 11, right? Am I mistaken? No? Good. So you have to somehow get into your head and in your whole system as a human. You have to get this, taking a row of the first matrix and inverting it, overlaying it to then, in this case, the second column. overlaying it, multiplying what you have there. So 2 times 2 minus 3 times 0 and 0 times 3. So that's easy because the two things cancel out and it remains with 4. And you need to get, and then you're done with already the first row. And then once you have the first row computed of your matrix product, you go on with the second row of A. So you're now with this and do that again over all columns of B. Yeah. So you now rotate 165 in your head, overlaid with 4 minus 1, 1, evaluate the products and sum up and get 3. Then again, you do it for the last thing combination that you have. So 1 times 2 plus 6 times 0 plus 5 times 3, it's 15. So you get 17. Yeah, so that is something you should practice. So you can practice that. So there are millions of practice tools online where you can practice multiplying matrices, so that you also know the correct answer. If you know how to program, then of course you can also just use the matrix product in MATLAB or somewhere to check your solution. There are also a couple of exercises, not many actually, in the script. Yeah, so you need to practice that. You need to I mean, it helps to understand the sum formula, but it's actually more important that you can multiply matrices of small size. So you can, of course, you can set yourself the task for the weekend to multiply a 10 by 10 matrix to a 10 by 20 matrix. Have fun. It will be annoying because you will make little errors all the time. So practice that for matrices of size, I don't know, 2 by 2 times a 2 by 4 matrix. So these numbers need to align, of course. 3 by 2 times a 2 by 1 matrix, maybe something else, 1 by 3 times a 3 by 2 matrix, things like that. Yeah, but please practice that. Otherwise, you will never feel good if you see a matrix product. And this is nothing that I can. This is their teaching ends in a way. This is something that you really have to do. And then you feel relaxed about matrix products. If you don't do that, you will never feel relaxed about matrix products. I can tell you. There is something that is quite helpful when starting with matrix multiplications, is that you can quite easily evaluate the size of the resulting matrix product. There's this little cheat formula in a way that if you have an n times m matrix, and you multiply it with an m times p matrix. So first of all, you know that these numbers need to always be the same. If this is not the case, the question is wrong. Then you can say the question is wrong. I don't answer that. But if these numbers are the same, then basically based on the mechanics of this sum formula, you know that the resulting matrix is of size n times p. And this is actually, this will be fairly helpful when we later see matrix products and sums that get a little bit more complex, because then you can always check, actually, am I doing the right thing here? So, or does maybe not what you are doing, but what you are seeing, does it make sense? So if it seems like the things that are being added are matrices of different sizes, then something is horribly wrong. And if it seems that matrices that are multiplied are not conforming to this inner dimension rule, then something is horribly wrong. And if this conforms, then you can quite easily also get a feeling of what the resulting matrix is without even computing the matrix. You just know the size of it. So that's fairly helpful. Good. I think I want to stop here. So we have talked thus far, sorry, scroll. We have talked about the definition. We've talked about addition and subtraction, scalar multiplication, and the most essential things, matrix multiplication. So that's really, and please practice that. If you don't practice it, you will be confused for the rest of the term. If you practice it, you will not be confused for the rest of the term. Matrix inversion, we will need, but we don't need right away. So I think I will introduce this when we talk about the Gaussian distribution, because in the Gaussian probability density function there is an inverse of a specific matrix. So I will introduce what the inverse of a matrix is at that point. I actually made a little supplemental video this morning that shows how to invert matrices by hand in case you're interested, but I will again bring that up once we come to the matrix inverse. And matrix transposition is really simple. It's also required in the Gaussian probability density function, so we will also talk about that. So that basically clears then the way to start the next session with simple linear regression. So we have essentially now everything that we need to formulate the deterministic aspect of the GLM and, in the special case of simple linear regression, which is good. Questions about definition of a matrix and the 3 or 4 matrix operations that we have talked about? No questions. Good. The multiplication thing needs a little bit of practice. So feel okayish when you don't when you don't feel quite comfortable about it right now. But please next week feel comfortable about it, because that's kind of the hierarchical approach we will take in this whole course, that what I introduced this week, everybody will have memorized next week. Otherwise, we don't make much progress. Good. So, there's one question.
Yes. Should we also have probability theory in it? Or are we?
Yeah. So that's a good question. So I think the outline that I give in the beginning, in terms of what happens in each session, depends a little bit. Okay. In general, I can only recommend that you study the winter term notes that you already have from last year, that you completely study this independently of me doing the teaching monkey here, and getting your head around all of this stuff, so that you can basically use these sessions here to revise what you have already studied on your own and maybe clarify questions. So that's, I think, a good use of this. So far, of course, things are relatively simple and easy to follow, but they build, and that's where the complexity comes in, so that when next week I just write down a matrix problem, I assume everybody knows what that is. It's maybe not really the case that everybody's familiarized with that. So the best use you can make of these sessions, and also looking at the videos online, there are videos online, is that you study on your own, independent of the whole thing here, and use this as kind of a revision of what you have studied. So yes, read everything. You have a lot of, I don't know what you have, but you don't have that much classes. You have every day 2 hours or so, so you have some time to study. Yeah? Good. Any other questions? No. Good. Then see you next week with simple linear regression. Goodbye.